Hello, and welcome to our video on star domains. Our quest for studying the antiderivatives of functions of a complex variable has led us to several places. We know it's particularly hard for an antiderivative to exist. The function has to be more than continuous, it has to be independent of path. And it also seems that the set on which the function is defined plays a large role. In particular, open sets and even domains, which is to say open and path-connected sets of holomorphic functions, don't guarantee that the function has an antiderivative on that domain. One kind of domain, a specialized version of our open path-connected sets that will facilitate the existence of antiderivatives, is the star domain. So in this video, we're going to talk about the definition and properties of star domains and work with some calculus of functions defined on star domains. So we say that a domain D is star-shaped, or a star domain, if there exists a point Z star in D, such that for all points Z in D, the line segment from Z star to Z is contained in D. And we call the point Z star a star center for D. More informally, you can reach any point in D by a line segment from the star center. So here is a picture of a star domain, and this is, I would hope, star-shaped and clearly a star. Where might we find the star domain, the star center here? Look right in the center. So I'm going to mark that point smack in the center of my big star by a little star. And say I take another point over on one of the arms of the star. Boop. There's a line segment between the star center and that point. Another point, another line segment, another point, another line segment, another point, another line segment, another point, another line segment. So you can always go from that center point, that star center, to any other point within our star domain by a line segment. Conversely, this annulus is not a star domain. So here the annulus is all points between the two concentric circles. And here's a problem. Say I take a point Z1 up here and a point Z2 down here. If I want to draw a line segment between Z1 and Z2, well, that line segment is going to pass through the center of the annulus, which doesn't live in the annulus. So I have that gap of the dotted line. So no matter what point I might pick to be my star center, maybe I'd think Z1 could be the star center, I can just sort of reflect around the center of the annulus and I'll find a Z2 such that the line segment from Z1 to Z2 isn't fully contained in the annulus. Any ball, however, is a star domain, and moreover, any point in the ball is a star center. So star centers don't have to be unique. You just need at least one of them. And here's a ball, here's a point Z0, here's another point Z. I can always draw a line segment from Z0 to Z. Here's a point W, can always draw a line segment from Z0 to W. So Z0 can certainly be the star center of the ball, and it looks here like Z0 is in fact the center of the ball. But W, I claim, could also be a star center. Here's a line segment from W to Z, got a line segment from W to Z0. So balls are always star domains. That'll be very important to remember. And the star centers don't have to be unique. Now here's a familiar picture. This is a triangle. So I have points Z1, Z2, and Z3 in the complex plane. And I'm calling this the triangle with vertices, or maybe I'll say edges, Z1, Z2, and Z3. And that triangle consists of all the points that I've shaded in blue that lies on this, well, triangle shape that we've known and loved since we were 5 years old. Let's think of a triangle in a more complicated way. A triangle is really a union of infinitely many line segments, where one endpoint of the line segment is Z1, and the other endpoint of the line segment lies between Z2 and Z3. So start over at Z1 and draw a line from Z1 to some point on the line segment from Z2 to Z3. That's one of these dashed or dotted lines here. Then sweep that line up and down the whole length of the line segment Z2 to Z3. And you've covered the entire triangle that I've shaded in light blue in my first picture. So triangles are just unions of line segments with very special endpoints. Here's the formal definition. The triangle spanned by the points Z1, Z2, and Z3 will be the set delta of Z1, Z2, Z3 that I'll define to be the following union. It'll be the union of all line segments of the form Z1 to 1 minus s times Z2 plus s times Z3 for s between 0 and 1. And I love this definition because it gives us a set-theoretic definition of a very familiar geometric shape. And the set-theoretic definition, yes, it's a union over uncountably many points between 0 and 1, but it's just the union of a bunch of line segments. And we can certainly draw and manipulate line segments very easily. And now let's look at the boundary of this triangle. That'll be the black path on the previous slide. This I'll call the triangular path spanned by Z1, Z2, and Z3, and it will be the closed curve that I'll denote as partial delta Z1, Z2, Z3, if we're thinking in terms of the LaTeX symbols. What is this triangular path? It's the line segment from Z1 to Z2, composed with the line segment from Z2 to Z3, composed with the line segment from Z3 to Z1. And so that's precisely the three line segments that form the outermost border of the triangle. And in particular, I see this as a closed curve because I start at the point Z1 and I finish at the point Z1. So the initial and terminal points of this triangular path are the same, and it's a closed curve. Now, here is a technical and important lemma. Star-shaped domains always contain sufficiently small triangles with one edge equal to the star center. Let's put this in a little more math speak. Say that D is a star-shaped domain, and its star center is Z star, and you take a point Z in D. Then there is a positive number H0 of Z. So H0 of Z is this positive number that depends on my other point Z. And if I take a complex number whose modulus is between 0 and this number H0 of Z, so 0 is less than or equal to the modulus of H is less than H0 of Z, then the triangle delta of Z star, Z, Z plus H is contained in D. So I have this triangle with one endpoint equal to Z star, one endpoint equal to my arbitrary point Z in the star domain, and one endpoint equal to Z plus H, which is just a little bitty perturbation of Z.